Hey everybody, hope you're doing well. This video will cap off week 7 of the 4th marking period, and it'll also be the last lesson of Unit 9. This is Section 4, and it will walk you through how to work with geometric series. So this will be similar to what you saw in the last video with arithmetic series, and it'll also tie in what you learned a couple of lessons ago about geometric sequences. So a lot of similarities, a lot of connections here to stuff you've done already in this unit. So just like an arithmetic series, a geometric series is also the result of adding the terms, but this time of a geometric sequence. You can see the same notation up at the top where we have finite series versus infinite series. It's the same as what you saw in the last video. Finite means you can count the terms that are there, and that's it. You can see that in the first example with 5, 10, 20, 40. In the example under infinite, 2, 8, 32, 128, that ... means the series goes on infinitely. All the notation remains pretty much the same as the last video here with arithmetic series. At the bottom, underneath the sigma, tells you what term to start with. The top tells you what term to end with. And you've got your rule after the sigma. You'll notice the formatting is a little bit different than what you saw in the last video because, again, geometric, the formatting for that does change a little bit here. You've got exponents involved, and it does, again, look a little bit different, but it's all the same idea. So just like the last video, we're going to go through the same 3 parts. We're going to look at how to write a geometric series using summation notation. We're then going to look at the long way to find the sum of a series, and then use a shortcut formula to find the sum of a series when you've got way too many terms to deal with. So, how to write a geometric series with summation notation. First thing I'm going to do here in example number 1, just like with arithmetic, I'm going to go ahead and write the sigma. So we can clearly see there are 4 terms. Okay, we can assume we're starting with the first term. And since we have 4 terms, we're going to end on the 4th term. Main thing to figure out is, what's the rule? So again, the key is geometric. Geometric rule, if you recall from a couple lessons ago, is this format. A sub n equals a sub 1 times r to the n minus 1. To write a geometric rule, you need the first term, so a sub 1, and r, which is that common ratio, aka what's being multiplied or divided to get all the terms. So, as you may also recall, these are a little bit easier to write because once you have the first term and the ratio, all you have to do is just plug them in, and that's pretty much it. So, the first term is 1. The common ratio is 3, because I multiply by 3 to get from one term to the next. And I have my rule. So 1 times 3 to the n minus 1. Put that rule after the sigma. I'm done. Okay, just remember, you don't want to multiply the 2 numbers that are there because the ratio is connected to an exponent. Again, as I reminded you many times in the video about geometric sequences, you don't want to do bad order of operations. So again, we leave those numbers separated. But that's your notation right there. So we're going to go ahead and do the same thing in the second example. So again, we start, the first term. So I'm going to put at the bottom here, I equals 1. Now, I do see 4 numbers, but I see a ... That ... means we are going to theoretically go on to infinity. So there would be an infinite amount of terms to the sequence. We'll put the infinity symbol on top. The big question is, what's the rule? So again, geometric, we have our format. So we need the first term, and we need the common ratio. So the first term is 625. The ratio, to get from one term to the next, you divide by 5. So to show division by 5, that's the same as the fraction 1/5. And there we have our rule. So it'd be 625 times 1/5, the n minus 1. And there is your notation. So again, very similar to what we did with the arithmetic series, but again, geometric has its own way to write the rule. And again, what's nice about it is it doesn't really take a whole lot of math. You just need to be able to identify 2 key things. So that's how we use the notation, how we write things using the notation. Now let's go ahead and take the notation and actually go find the sums. So again, we'll start with the long way to do it, and then we will do it the short way with the formula. So here we have a starting term of 2. So we're going to start with the second term and go all the way to the fifth term. So if I'm doing this the long way, that means I'm going to start by plugging 2 in for the exponent, then 3, then 4. Again, make sure you plug it into the right spot. So again, your n value is what's being replaced, and then the 5. So we're going 2 through 5. Now, if we're doing this by hand, the long way here, you might want to make sure you do some PEMDAS. Again, if you want to show all the steps, you'd condense the exponents down, you'd subtract those, apply them to the number it's right next to, and then multiply by 2. Again, you have nice graphing calculators that should be able to do all this here in one step. If you do it correctly, these are the 4 terms you should get: 6, 18, 54, and 162. If I'm finding the sum of those series, I'm going to add them together, which will result in a sum of 240. In the second example, same exact thing. If I'm doing this by hand, we are starting with the 4th term, ending on the 7th term. So I would go ahead and plug in 4 through 7 in for n. So you can see here I'm doing just that. And again, PEMDAS-wise, you would do the same thing. Subtract the exponents together first, apply it to the 2, because it's directly next to it, and then take that result, multiply it by -1. The answers you would get for that would be -8, -16, -32, and -64. So you would add those together, and again, they're negative. Again, you could do plus negative if you really want to show it out like this. You just subtract them. It's all the same thing. Again, you put them all together, you get a sum of -120. So again, plug and chug is not bad when you only have to find and work with a handful of terms and add them up. But again, if you have to do 10, 15, 20, however many, it's a lot easier to have a shortcut and use a formula that'll help condense everything. So at the bottom here of your notes and on the second screen that I have here, let's take a look at the formula we're going to use. So to find the sum of a finite geometric series efficiently, we're going to use this formula here in the box. S sub n equals a sub 1 times 1 minus r to the n over 1 minus r. Again, these are all variables we have dealt with in some capacity. S sub n, again, is that notation. It just says the sum of n number of terms. A sub 1, value of the first term. N is the number of terms we're working with. R is the common ratio. So, the one thing again about this is all of your pieces of info are going to be pretty much right there in front of you. There's even less math to do than what you had to do with arithmetic, because everything is nicely laid out. So, let's go ahead and identify 3 things. We need to identify how many terms we're working with. What's the first term? What's the ratio? So, if we look here at finding the n value, so how many terms? Starting from the first term all the way to the 13th term. So if I'm doing terms 1 through 13, there's 13 terms. So again, I'm making this easy on you because you'll notice everything is I equals 1, so it'll be easy to count how many terms you have. So the n value, 13. Now, we're not going to have to do a lot of work if you know the format of the geometric rule, because it is so specific and it doesn't really require any simplifying. If you look at this, inside the parentheses here, next to the exponent is your ratio. The number in front of the ratio is your first term. So the A1 is 3, the R is 4. That'll be the case every single time. So again, knowing the formatting of these is very helpful because you can just pull the information right out. You don't have to do any crazy amount of math to figure these things out. The ratio is always directly next to the exponent, the first term will be to the left of whatever the ratio number is. Okay, so it'll be in the front of the problem. You've got the three things that you need. Now let's go ahead and use our formula. So again, different formula this time. S sub n equals a sub 1 times 1 minus r to the n over 1 minus r. Now, before we start plugging in numbers here, I suggest, again, plug them in, see what you come up with. I'm going to warn you, because we are doing geometric series, you are going to get some very, very big answers most of the time when you do this. Because, again, exponents, once we start getting high up into powers, that means you start getting really big numbers. And if you add lots of really big numbers together, you get even bigger numbers. So just be aware, if you get 8, 9, 10-digit numbers, doesn't mean you're doing it wrong. You'll see here in a minute. So we're finding the sum of 13 terms, so we're plugging in 13 for n. The a1 is 3, 1 minus r to the n, so 1 minus 4 to the 13th power over 1 minus 4. Now, keep in mind, 4 to the 13th is not 4 times 13. Please do not make that goofy mistake. You punch it in. Your numerator, again, I'm just doing 1 minus this so I don't have to take up a whole bunch of space here with these big numbers. 1 minus 4 to the 13th power comes out to negative 67,108,863 all over negative 3. Again, I'm going to divide it. So my fraction comes out to 22,369,621. Multiply it by 3. You'll notice I get pretty much the same number I had to start with, because the 3 and the negative 3 almost in effect cancel each other out. So the sum of the first 13 terms of this geometric sequence is 67,108,863. Gigantic number, but that's what you're going to see here with these geometric series. So let's go ahead and repeat that process here with the other two problems. Again, you see that? Maybe try the next one here on your own. So again, we're going to find how many terms, identify the first term, identify the ratio. So, starting from the first term, ending on the 20th term means I have 20 terms. That's my n. My a1 is in the front of my rule. The r is stuck to my exponent. So the a1 is 2, and the r is negative 3. I got everything I need to go solve. So plug in the 20 for n, the 2 for a sub 1. Notice the ratio is negative. Put that in parentheses, because if you don't, my gut tells me you're going to mess up how you punch this in the calculator with the exponent and get an answer that is very, very wrong. So you notice here, because I'm substituting in a negative, I'm putting parentheses around it. You should too, and then you won't make goofy mistakes when you ultimately go straight to the calculator. So, my numerator in this case, this comes out to a pretty gigantic number that I have written out here on my paper. Looks like it comes out to 3,486,784,400, you know, regular number stuff, all over 4. We'll go ahead and divide. Give me negative 871,696,100. Multiply that by 2. The sum of the first 20 terms of this geometric series is negative 1,743,392,200. Hopefully you're enjoying this practice with your place value as well. Now again, just like I've said in all the other lessons, you don't necessarily need to show every layer of that PEMDAS. What I'm looking for is that you have identified the correct numbers. You're plugging in and showing where all the numbers go in the formula. Whatever PEMDAS you want to use is fine, but the more work you show, in case you screw something up, you'll lose less points, because I'll be able to see where you made a mistake. All right, final problem here. Same deal, number 3. Starting at the first term, working our way to the 12th term. That means there are 12 terms. My A1 in front of the rule, my R directly next to the exponent. So my first term, A1 is 6, my R is 4. So once again, here's my formula. And let's go ahead and plug stuff in. So 12 goes in for N, 6 for the A1, 1 minus 4 to the 12th in the numerator, and 1 minus 4 in the denominator of the fraction. So these numbers aren't as excitingly big as the last problem, but we'll get 6 times in parentheses here, negative 16,777,215 over negative 3. Simplify the fraction, we'll get 6 times 5,592,405. And then we'll multiply that by the 6. The sum of the first 12 values of this geometric series comes out to 33,554,430. So again, another big answer. And it doesn't technically mean when you do these that you're always going to get these gigantor answers, but I will tell you the bigger the n value is, again, since that's where the exponent is in this formula, the much larger the answer is going to get. So the bigger the n value, the bigger your answer. So, graded assignment that goes with this, very similar to the one you just did for the last section. 4 questions again. First 2, showing me that you can write a geometric series using summation notation. The other 2, just like the problems you see here on the screen, where you are finding the sum of the geometric series. Again, do show me some level of work. Whatever you need to show me there is fine with me, but show something. As always, if you have any questions, send me a message on Schoology, shoot me an email, or stop by my office hours on Zoom. I'll be more than happy to help you out. Otherwise, thanks for taking the time to watch this. Stay safe, stay healthy, and we'll see you next time.